Good afternoon, and thank you for coming. My name is Kostya Serebryany. I work at Google in the Sunnyvale office, and my team has been dealing with memory safety in C and C++ for the last decade. My today's talk is called Memory Tagging and how it helps C++ memory safety. I hope I will convince you that we have a path forward with C++ and memory safety. I will remind you what memory safety is, in case you don't remember. I will explain the general concept of what we call memory tagging or memory coloring. We will discuss 3 existing implementations of memory tagging, including one that has been just announced by ARM 8 days ago. And we will briefly discuss how this affects security of the C++ code. So, first of all, a statement. Memory safety in C++ is a huge mess. Raise your hand if you agree. Okay, so I don't have to convince this audience. We have all sorts of use after free and buffer overflow on heap, on stack, and globals. And we still basically don't have any general protection against it. And if anyone thinks that the newer C++ standards give you any better protection than before, I have to disappoint you. C++ 17 actually makes certain forms of memory safety bugs less obvious and more frequent. This is the slide I've shown a year ago at CppCon. I don't think anything has improved since then. There is a class in C++ 17 that is misnamed. It should have been called std use after free. And for some reason, it is called std string view. Raise your hand if you can spot the bug. For those who cannot spot the bug, I will explain. The second line of the code snippet creates a temporary string object that is destroyed right after the semicolon. But the string view captures the pointer to the guts of the string, and then you use it later. This is a use after free on heap or use after free on stack, depending on how exactly the string is implemented in the standard library. We keep seeing these memory safety bugs for many, many years now. And the overall picture doesn't change from year to year. For example, if we just take the Chrome browser, which is a huge C++ application, every time we release a new version of Chrome, we fix some number of security bugs, and most of the high priority security bugs are memory safety bugs. This is a text from the Chrome release in July. 5 out of 5 high priority security vulnerabilities in Chrome were memory safety bugs. So this is not just theoretical. We're facing this problem for real. How many of you have heard about a tool called AddressSanitizer? Okay, I can skip a few slides. For those who haven't heard, this is a tool based on compiler instrumentation. It inserts a few instructions before every load and store. Those instructions check metadata attached to memory, and so we can catch buffer overflows and use after free. And this slide probably, hopefully, describes the general idea. So if we, for example, malloc or new 24 bytes, then the user will get a pointer to a memory that is marked addressable. So this is 3 times by 8 bytes. And there will be chunks of memory adjacent to the buffer, to the left and to the right, that are marked unaddressable. We call those red zones. And so if the code touches P sub 24, which is already unaddressable byte, we catch the bug. When we free the memory or delete the memory, we mark the entire chunk as unaddressable. And then we try to keep that memory in quarantine as long as we can, meaning that the following many malloc invocations will not return the same address. So we improve the probability of catching use of the free. So ASAN, as far as I can tell, is pretty widely used as a testing tool, but it has a very significant limitation when it comes to using ASAN in production. Generally speaking, you cannot use ASAN in production. Some people do, but this is pretty complicated effort. The main reason why it is so complicated is because ASAN has 2x overhead, roughly, in memory, CPU, and code size. It is very hard to deploy anything that expensive in production. The overhead is caused by the compiler instrumentation that we insert around every load and store, and also by the shadow, by the red zones, and by the quarantine. It is also not a strong security mitigation. It is easy to bypass for the attacker if the attacker wants to bypass ASAN. So now let's discuss the other approach. The approach is typically called memory tagging or memory coloring. And I will try to explain the entire thing, the entire topic of the talk on just this one slide. So pay attention, please. First of all, this approach, unlike ASAN, only works on 64-bit architectures. So if you care about 32-bit architectures, no luck. We have to have some magic way to associate a metadata with every n bytes of memory. For example, we want to have a 4-bit metadata or tag attached to every 16 bytes. We can play with these numbers. We can have more bits in the tag. We can have larger granules, larger chunks of memory which have a tag. But the idea doesn't change if we change just these numbers. The next important thing is that when we have a 64-bit pointer, not all of the bits in the pointer are actually used. On today's typical x86 hardware, you use 48 bits of the pointer and the remaining 16 unused. Similarly on ARM and other 64-bit architectures. So when we do memory tagging, we also use some of the bits in the pointer to store a tag in the pointer. So we have two tags, one associated with the memory and one associated with the pointer. Then when you allocate memory in malloc or when you enter a function for a local variable, you need to tag that memory and also tag that pointer with the same tag. And then whenever you load a store, you have to check that these tags match. If they don't match, you trap. So this allows you to find most of the memory safety bugs like use of the free and buffer overflows. Here's the workflow for malloc. So if you want, suppose you have the memory tagging system implemented on your hardware. The malloc will need to do very, very little extra work on top of its usual work to support memory tagging. First of all the memory chunks, all the heap objects returned by malloc have to be aligned by the granularity of memory tagging, so 16 or 64, depending on the implementation. Then malloc will have to choose a tag. If a tag is a 4-bit, you basically choose one of 16 values. You can choose it randomly. The next step is to tag the entire chunk of memory that you're returning, and also tag the pointer. This is basically it. No magic. When you free the memory, you can also optionally retag the memory to some other tag. And let me try to demonstrate it with a little bit more colors. And by colors, I mean tags, of course, but they are colors. When you're requesting 20 bytes from you, the first step that the memory allocator does, it aligns the requested size by the tagging granularity. And in this example, I'm using the 16 bytes granularity, which means that 20 bytes we have to align up to 32. So malloc allocates 32 bytes of heap memory. It then chooses a tag. In this case, the tag is hexadecimal A, or green. And so malloc will put this green color, or green tag, into both the memory, these two 16-byte chunks, and the pointer. So the pointer will look like this. It has the tag in the upper 4 bits, and then the usual pointer stuff. The adjacent memory chunks are already colored by previous heap allocations. And they have some other colors. Since there are only 16 colors, if we use 4-bit colors, it could be the same color, but there is a large probability that this color is different. And so when the code is trying to dereference P sub 32, it means that we're accessing blue memory with green pointer. And if blue is not equal to green, we get a failure. Very similar thing happens on delete. Whenever we delete a heap chunk, we just recolor all the memory for that heap chunk. And if there is a dangling pointer that is still green, and we try to access the memory that used to be green but not anymore, it is purple now, we will have a trap. Any questions so far? How do I tag the memory? Hold on a bit. I will explain how I tag the memory. So I will certainly get back to it. Don't worry. As I already mentioned, the probability of detecting a bug is not 100% because we only have so many different tag values and we have much more different memory chunks. So the probability of detecting a bug depends on the tag size. If the tag size is 4 bits, then you only have 16 different colors, and in 15 out of 16 cases, you will detect the bug. So it's about 93%. If you have more tag bits, the probability goes higher. A few words about precision of buffer overflow detection with this approach. So if you allocate 20 bytes, it means that you are actually allocating 32 bytes by malloc. And so if you're trying to access incorrect memory within the same granule, within the 16 bytes of allowed memory, then no luck. This approach doesn't have this level of accuracy. If you are trying to touch memory that is in adjacent granule, like P sub 32 in this example, or P sub -1, you get the memory error detected. And depending on this software allocation strategy, you can have the detection at 100% probability or 90 something. If you're trying to dereference this pointer with some wildly off index, then the probability is roughly 90+%. The software could choose different strategies for allocating tags when allocating heap or stack memory. We think that the best strategy is actually to just allocate a random tag. But there could be different other strategies. You can have a dedicated tag that says match none, meaning that this memory is never allowed to be accessed by anyone. Or you can alternate odd and even chunks to make the probability of buffer overflow detection to be 100% for linear buffer overflows. All the same story applies to stack buffer overflow detection and stack use after return detection, except that now the implementation should not just update the malloc function, but it also has to do a little bit instrumentation in the compiler. I will not go deeper into this. And the same story for global buffer overflows. You have to tag your globals. First thing that I want you to know about the scheme is that it doesn't have any false positives. So If you find anything with this scheme, it's a real bug. Go fix it. Now, how do we actually implement this thing? And one of the implementation problems is that we are using or abusing bits in the address. Thanks to a marvelous feature that exists in today's hardware on ARM64, we can just do it. The feature is called top byte ignore. You can put any garbage into the top byte of the address on ARM64, and the hardware will just not look at it. So on ARM64, this part of the implementation is pretty easy. On x86 64, it's hard enough that I don't advise you to go there today. It's pretty painful. Before I move further into the actual implementations, I want to give a quick comparison of memory tagging as an approach with ASAN as an approach. So what are the differences? First of all, memory tagging has very small memory overhead compared to ASAN. ASAN is roughly 2x memory overhead, and memory tagging, depending on the tag size and the granularity, is either several percent of memory or less than 1% of memory. So it is really tiny. The two other benefits of memory tagging is that memory tagging is more sensitive to detecting buffer overflows that happen way beyond the bounds of the object. And memory tagging is more sensitive to use after free when the free happens much, a lot of time after the free. The use happens much later than the free. So memory tagging is more sensitive. And optionally, as a side effect, memory tagging forces all the memory to be initialized, so you don't have uninitialized memory anymore. ASAN still has its own benefits. First benefit is that ASAN is 1 byte precise for buffer overflows. And second, it is more portable. It works on today's hardware in 64 and 32-bit. Now let's move to the existing implementations, and I hope I will explain how do we actually tag the memory, at least in general idea. So first of all, there is SPARC ADI. It is an actual hardware implementation that exists in the shipping CPUs for at least 2 years. They use 4-bit tags per 64 bytes of memory. They have special instructions that allow you to tag the memory and read the tags. The documentation doesn't tell you where these tags are stored, so I cannot tell you how do we tag the memory, like how does it physically work. Although everyone's suspicion that they're using ECC bits to store the tags. But you don't need to know how it works in order to use it. To use it, you just use an instruction. We have tested this implementation pretty extensively, and in short, it works great. But it has two problems. First problem is that the granularity of tagging is 64 bytes, which means that the malloc has to over-align too much, and so we spend too much memory, up to 20% more memory because of over-alignment. Who can guess the other problem with this implementation? Anyone? Okay, the problem is that this is implementation in SPARC. And I don't have any SPARC in production, or we don't ship any SPARC CPUs in client devices. This is the major problem for us. The implementation is amazing, we cannot use it. And so we have actually implemented something we can use today on today's hardware. We call it HWASAN, or Hardware Assisted ASAN. It is currently in the Clang LLVM toolchain. The tool is only really usable for ARM64 because, as I mentioned, ARM64 has this magic feature called top byte, We use 8-bit tags per 16 bytes of memory, which means we have 6% extra memory usage. But we use compile instrumentation to actually check the bugs at runtime, which means that we have 2x CPU overhead. This is testing tool very similar to ASAN. The biggest advantage is that it has very low memory consumption. And we also have this for the Linux kernel. Patches are under review. Any questions so far? OK. I'm very happy to tell everyone here from this stage that 8 days ago, ARM has announced what they call memory tagging extension. It is an actual hardware implementation in the upcoming ARM 8.5 architecture. It doesn't exist in hardware today, so I'm eagerly waiting for it to appear in the real hardware. They use 4-bit tags per 16 bytes, which is very good balance. You have enough data and you have small enough granularity. It is suitable for efficient stack instrumentation, so you get both stack and heap related bugs. And you don't have to overline malloc, so very little extra RAM overhead. It has just a few instructions that you may want to use to set the tag and to set the tag in the address and to set the tags in the memory. And again, the instruction set does not specify where the tags are actually stored. This is left to the implementation. So how do we tag the memory? We use the instruction to tag the memory. How does it actually work? No idea. And it will probably vary between the implementations. As a side effect, and as already mentioned, when we tag the memory, we can optionally also initialize the memory itself. And with the hardware implementations, it doesn't have any extra cost. So if you're using memory tagging system, you initialize all your memory at no extra overhead, and you just don't have uses of uninitialized memory anymore. So what is it good for? We think that memory tagging is a very strong alternative to AddressSanitizer, ASAN, because it consumes much less memory and it is also more sensitive to certain bugs. We believe that it is very useful for crowdsourced bug detection in production. This is certainly true for hardware implementations like the existing SPARC ADI and the proposed ARM memory tagging extension. It is to some extent true about our software implementation, HWASAN. HWASAN has large CPU overhead, so not always, not everywhere. We also believe that memory tagging is a very strong security mitigation that you can deploy in production against attackers. Probably the strongest than anything we have today combined. Why do we think so? So first of all, it is precise 100% reliable mitigation against linear buffer overflows. Things like Heartbleed and Ghost Bug and lots of other publicly very popular bugs are linear buffer overflows. We can mitigate them completely. We can also mitigate use of the freeze probabilistically, which means that the attacker will have to launch attack many times before the attacker succeeds. Most attackers will be discouraged, we hope. There are some ways to reliably bypass memory tagging, but the bottom line is that in order to bypass memory tagging to attack a memory safety bug in C++, you have to have a reliable exploitable bug of some other class. And we have to deal with them anyway. So there is a little bit of catch-22. If you want to bypass memory tagging, you have to have an exploitable bug. But most of the exploitable bugs are protected by memory tagging. And as a mitigation, it also works for uninitialized memory. We think that memory tagging will find more uses outside of just memory safety and security mitigation. We're certain that memory tagging can be used as infinite hardware watch point at very low cost. We also think that the Java people or garbage collection people will find ways to abuse it for garbage collection efficiency. And I'm actually very eager to hear from you offline after this talk. What else can we use memory tagging for? I would normally have a summary slide, but I don't. I have a homework slide instead. So I have 2 pieces of homework for you, and I will ask all of you next year in CppCon. First of all, please ask your favorite CPU vendor to implement some form of memory tagging. If your favorite CPU vendor uses ARM instruction set, then you can just point them to the public instruction set extension. And my second piece of homework, take a look at your favorite C++ memory safety bug or exploit or vulnerability. And do the thought experiment. Is it mitigatable? Is it detectable by memory tagging? And is memory tagging a strong mitigation for this case? This is all. And thank you. Questions are welcome.
Hi. Sorry. Question is the following. So due to the limited number of platforms where this is actually implemented, and let's say you can build your framework or any application that you're using in a sandbox environment. Let's say you, for example, with ASANs, you might not use ASANs in production, but you have a debug environment and you have like maybe a Docker that sets it up and then you run it and then you get the output. So for those ARM instructions, could you use like a QEMU emulated environment where you would apply your memory tagging and then you can catch right? Have all the benefits without actual hardware support on the production?
It's probably not worth using it in QEMU because if you're ready to hit the 30x slowdown from QEMU, you can just use ASAN and you're fine. It will be slightly less sensitive, but at this performance hit, you just better using ASAN. The major benefit from memory tagging is if it's in hardware, if it's extremely fast, and you can use it all the time.
But as I understood, it provides better guarantees, right? And has this, well, probabilistic, independent of how many bits it is the error from the memory that they actually use.
That's correct. Memory tagging is more sensitive to certain types of bugs, but it only matters, really? It only matters if I'm running it in production. You cannot use QEMU in production. No. And I'm told that the session is over. Is it? No? 2 more minutes? OK, 2 more minutes.
Thank you.
Thank you for the introduction into memory tagging. In order to understand where to aim for the future, what would your expectation like, for example, in 5 years? Should we expect that it becomes like a production and widely used feature for any case, or it still stays the same thing as, for example, because there is an overhead on CPU in order to use memory tagging and validation, and therefore we use it only for development? So in other words, like, would CPU manufacturers aim to re-architect their devices in order to make it cheaper to use everywhere?
Will we have memory tagging everywhere in 5 years? It depends on you guys. If you apply pressure to your hardware vendors and your software vendors, it will be widely used in 5 years.
Thank you.
If you don't, it may or may not happen.
I'm still digesting a little bit how the tagging itself plays out. I'm going to try to ask 1 or 2 questions here. Maybe you can catch if I'm smelling something appropriate or not. My thoughts go to, I've seen warnings all the time, pointers, alias pointers for that matter, and pointers into raw memory that are just random offsets from other areas of memory. Are there any opportunities here for tags to be, when we copy pointers, do we copy the tags? Or if I'm misinterpreting that the tag is part of the data rather than as part of the pointer.
The tag is both part of the data and of the pointer.
So
And
would we have aliasing issues allow us to, if I try copying to another pointer that's pointing to the same memory location but isn't exactly the same pointer, would I be able to run into issues there? You said no false positives earlier.
no false positives. It just works. So if you copy pointer, you just have the same tag and the same pointer. No false positives. We run the entire Android platform with our software implementation of memory tagging. It just works.
Thank you.
In the hardware-assisted tagging scheme, you said there's about 2x CPU overhead. Does that include the time required to generate the random tag?
Yes, generating random tag is not very expensive. And we, in our software implementation, we don't really generate it truly random. We just take some of the random bits from SP. In the software implementation, all the cost is due to compile instrumentation of loads and stores.
Okay, so the random source is from SP, okay.
Yeah. Yes, I'm told the session is over, but I'm here in case you have questions offline. Thanks again.